Transformation of functions. Often, when given a problem, we try to model the scenario using mathematics in the form of words, tables, graphs, and equations in order to explain or solve it. When building models, it is often helpful to build off of existing formulas or models. Knowing the basic graphs of your toolkit functions can help you solve problems by being able to model new behavior by adapting something you already know. Unfortunately, the models and existing formulas we know are not always exactly the same as the ones presented in the problems we face. Fortunately, there are systematic ways to shift, stretch, compress, flip, and combine functions to help them become better models for the problems we are trying to solve. We can transform what we already know into what we need, hence the name, transformation of functions. When we have a story problem, formula, graph, or table, we can then transform that function in a variety of ways to form new functions. Shifts. Example 1. To regulate temperature in a green building, airflow vents near the roof open and close throughout the day to allow warm air to escape. The graph below shows the open vents V in square feet throughout the day, T in hours after midnight. During the summer, the facility's staff decides to try to better regulate temperature by increasing the amount of open vents by 20 square feet throughout the day. Sketch a graph of this new function. We can sketch a graph of this new function by adding 20 to each of the output values of the original function. This will have the effect of shifting the graph up. Notice that in the second graph, for each input value, the output value has increased by 20. So if we call the new function s of t, we could write s of t equals v of t plus 20. Note that this notation tells us that for any value of t, s of t can be found by evaluating the v function at the same input, then adding 20 to the result. This defines s as a transformation of the function v. In this case, a vertical shift up 20 units. Notice that with the vertical shift, the input values stay the same and only the output values change. Vertical shift. Given a function f of x, if we define a new function g of x as g of x equals f of x plus k, where k is a constant, then g of x is a vertical shift of the function f of x, where all the output values have been increased by k. If k is positive, then the graph will shift up. If k is negative, then the graph will shift down. Example 2. A function f of x is given as a table below. Create a table for the function g of x equals f of x minus 3. The formula g of x equals f of x minus 3 tells us that we can find the output values of the g function by subtracting 3 from the output values of the f function. For example, f of 2 equals 1 is found from the given table. G of x equals f of x minus 3 is our given transformation. g of 2 equals f of 2 minus 3 equals 1 minus 3 equals negative 2. Subtracting 3 from each f of x value, we can complete a table of values for g of x. As with the earlier vertical shift, notice the input values stay the same and only the output values change. Try it now. The function h of t equals negative 4.9 t to the squared plus 30t gives the height h of a ball in meters thrown upwards from the ground after t seconds. Suppose the ball was instead thrown from the top of a 10-meter building. Relate this new height function, b of t, to h of t, then find a formula for b of t. The vertical shift is a change to the output or outside of the function. We will now look at how changes to input on the inside of the function change its graph and meaning. Example 3. Returning to our building airflow example from the beginning of the section, suppose that in fall, the facility staff decides that the original venting plan starts too late and they want to move the entire venting program to start 2 hours earlier. Sketch a graph of the new function. In the new graph, which we can call f of t, at each time the airflow is the same as the original function, v of t was 2 hours later. For example, in the original function v, the airflow starts to change at 8 a.m., while for the function f of t, the airflow starts to change at 6 a.m. The comparable function values are v of 8 equals f of 6. Notice also that the vents first opened to 220 square feet at 10 a.m. under the original plan, while under the new plan, the vents reach 220 square feet at 8 a.m. So v of 10 equals f of 8. In both cases, we see that since f of t starts 2 hours sooner, the same output values are reached when f of t equals v of t plus 2. Note that v of t plus 2 had the effect of shifting the graph to the left. Horizontal changes or inside changes affect the domain of a function, the input, instead of the range, and often seem counterintuitive. The new function f of t uses the same outputs as v of t, but matches those outputs to inputs 2 hours earlier than those of v of t. Said another way, we must add 2 hours to the input of v to find the corresponding output for f. F of t equals v of t plus 2. Horizontal shift. Given a function f of x, if we define a new function g of x as g of x equals f of x plus k, where k is constant, then g of x is a horizontal shift of the function f of x. If k is positive, then the graph will shift left. If k is negative, then the graph will shift right.